Morning we have seen the syllabus. So in the syllabus, what are the core subjectives we have discussed in the morning? Around 6 core subjectives are framed, which are based on the 6 modules. Okay, and in the first module we have the seismology and earthquake. We will be dealing with the structure of the earth, the continental drift, plate tectonics, the faults, elastic rebound theory from which the earthquakes will be generated, and the seismic waves and their characteristics, the size in terms of intensity and magnitude, strong ground motion, and seismic zoning map of India, and finally the seismic hazard assessment. Okay. So it has 6 hours. Within that, we have to complete the first module, and after that, we will be moving to the second module. In that, we will be the studying the principles of earthquake resistant design, then response spectrum theory, which is very essential for the design of the structures as per IS 1893 Part 1, and application of the response spectrum theory to the seismic design of the structure, and capacity design principles, design criteria for strength, stiffness, and ductility. Okay, so in that the capacity and the ductility, it simply refers the strong column weak beam criteria. Okay. So in a building, if you design based on the column is very strong and the beam is weak, then it will be good. It will survive for a long time. In reverse, the beam is strong and the column is weak. If we design in such cases and the column gets failed, definitely the entire collapse of the structure will occur. So to avoid that, we prefer strong column weak beam criteria. Okay, so in order to achieve the strong column weak beam criteria, there are certain design rules and recommendations are provided in IS 13920. Okay, so IS 1893 Part 1 2006, this one, IS 1893 2006 Part 1. This is for analysis of the structure. Okay, so how do we analyze the structure for the seismic forces? There are 3 types of analysis. Okay, so one is equivalent static, and second one response spectrum, and the third one time history analysis. These 3 will be based on force-based method of the design. Okay, so the amount of force which will be generated during the certain earthquake. So for that force, the analysis and design will be carried out. In reverse, performance-based design is also there, but there is no such recommendations are provided in IS 1893 Part 1, but it is preferred to consider performance-based design in the structural design. And so 1893 Part 1 2006, the amount of force will be generated during the earthquake will be calculated. Okay, so 13920 2006 16, this is the ductile detailing of the RC structures. Okay, subjected to the forces which are calculated based on 1893 Part 1. Okay, so this is for design and this is for analysis. 1893 2016 for analysis, 13920 for design purpose. Okay, so this will ensure ductility of the structure. Okay, so if you estimate the forces, seismic forces based on 1893, and design your structure, RC structure for based on IS 456, then it will not ensure the ductility of the building. Okay, so but if you design based on IS 13920, because the codal provision is itself is there, it is ductile detailing of reinforced concrete structure. Okay, so your ductility of the building will be ensured if you design based on this code IS 13920. So the major difference is your joints will be properly detailed. Beam column joints will be properly detailed. So detailing is nothing but is, of course, at the joints only shear force will be maximum. For that shear force only we will be providing the stirrups. Okay, so for that, shear forces will be calculating the stirrups and its spacing. Okay, and at center of or mid span, your shear will be very less, so we will be providing the nominal spacing. Okay, whatever the maximum spacing is allowed, that will be provided based on IS 456. But in case of IS 13920, closely spaced stirrups will be provided at the joints, not only in the beam but also in columns also for particular length. Okay, so it will ensure ductility of the beam column joints, so that the structure will be behaving more ductile when it is subjected to seismic forces. Okay, so you understand? So are you all listening?
Yes, sir.
Okay.
Sir.
Yes, sir.
Okay, thank you. So, this strong column weak beam design criteria is there in the module 2. So module 3, 4 and all we'll see later. So first let me get into the course, seismology and earthquake. So it is introduction to earthquake engineering. So in this first module, we have the contents engineering seismology, seismic zoning map of India, strong motion studies, and strong motion characteristics, evaluation of seismic design parameters. Okay. So in engineering seismology is, of course, we'll be knowing about the earth and its structure, interior of the earth, what is happening. We know very well earth is of 3 parts. It consisted of 3 parts. One is mantle, suppose starting from crust, and middle one is mantle, and the inner one is core. But what is happening inside? What are the material present in it, and what is happening inside? So that we'll be studying. And what is continental drift? Okay, so what is continental drift? Convection currents. So what is happening inside the earth? That is called convection currents. It is the thermomechanical behavior of the viscofluids which is present inside the earth. It will create convection current. So because of that, the plates which are floating in the crust level will be moving. Okay, so that movement of the plates which are on the crust level will be based on the convection current which is developed inside the earth. Okay, so how it is being developed, the convection currents. Okay, and what are the materials present inside the earth and all we'll see. So what is plate tectonics? And elastic rebound. So this, based on this elastic rebound only, the earthquake will be generated. And what is fault, and what are the other sources of the earthquake, and what are the location of the earthquake, seismic waves when the earthquake generates, what are the waves will be generated. So seismic waves will be generated. There are 2 types of waves: body waves and surface waves. So body waves, it will travel inside the earth only, and the surface waves, some of the secondary waves which travel at the surface of the crust, the earth only. Okay, so its behavior will be a little different than our the body waves. And what are the effects of the earthquakes to the buildings and other parts of the earth? And measurement of the earthquake, that is already mentioned when I explained the course syllabus. That is intensity and magnitude. So based on these 2 measures, the earthquake will be estimated. And seismographs, how do we estimate this earthquake? In terms of 3 parameters. Earthquake is a dynamic force. It is a dynamic in nature. Dynamic force, we know that dynamic is nothing but it will be varying with respect to time. Okay, so time is the constant in x-axis. Okay, but during earthquake, your ground will be vibrated. The ground, the plates, the plate which are present at the crust, that will be vibrated. So during that vibration, the movement of that plate during that vibration, displacement of the ground will be present, and the speed, the acceleration of the acceleration and velocity of that vibration, that plate movement, that will be measured. So here three parameters will be recorded during earthquake. One is displacement of the your plate or the ground, or and velocity of that movement, as of course acceleration of that movement. These three will be recorded during earthquake. Okay, so these three parameters or the amplitude, it will be in the y-axis. Since the dynamic force, it is varying with respect to time, so it will be x-axis. Time will be in x-axis. So three records will be obtained from this earthquake, and it will be recorded using seismograph. Seismograph, seismograph, it is not a graph actually. It is an instrument to measure these three parameters, right? So seismograph, it's an instrument to record these parameters. The measured response or the measured plots or seismogram. Okay, seismograph, it's an instrument, seismogram or the plots. Okay, now classification of the earthquake based on the magnitude, based on the place where the earthquake waves generated, whether during the collision of the plates, at that point the earthquake is generated, or inside the plates, somewhere inside the plate the earthquake is generated. Based on that, it is intraplate earthquake or interplate earthquake. So like that it can be classified, and based on the magnitude, low magnitude earthquake, medium earthquake or severe earthquake, so like that we can classify the earthquakes. Now what is there inside the earth? Earth is a layered structure. Of course we know that from the outermost end to the center of the earth, the material is not uniform. The atmospheric matter is of the least density material, and due to gradual increase in density and temperature inside the earth increased, because of which the material which present inside the earth started getting separated depending on the variation of these densities. So the heavier material which is present at the upper the crust level to sink towards center of the earth, and the lighter ones to move towards the surface. So later the lighter material, it will get cooled and solidified to form the crust, because inside the earth the temperature is not uniform, the density is not uniform. Okay, so everything will be varying, and the density, temperature, everything will be increased as you go inside the earth, okay, towards the core of the earth. Now the dense material, not dense material, the heavier material or the solid material which is present at the top of the earth, and due to difference in temperature, due to difference in densities, so the heavier material which is present at the top, it will try to move down, and the lighter material, it will try to move up. Okay, so once the lighter material come above the earth or at the surface of the earth, because of the difference in temperature, because at the surface the temperature will be very less, atmospheric temperature only. So because of that temperature difference, the lighter material, when it comes upside, when it comes above, it will get cooled and solidified. Then only it will form the crust. So this is the schematic view of the earth. The upper one is the crust. It will have very less thickness, and inside mantle, then core. Is of course again mantle also can be again classified into two parts: upper mantle and inner mantle. Just like outer core and inner core, like that. Outer mantle and inner mantle also it can be classified based on the thickness and density variations. So the thickness of your the crust is 5 to 70 kilometer, and the outer mantle it is 2900 kilometer, and inner mantle then again core is of it is 1370 kilometer radius. Okay, so here there is no thickness, that is why the radius of this inner core is given 1370 kilometer. Now your diameter of the earth along equator it is 12740 kilometer, and along pole it is 12,700 kilometer along poles. The specific gravity at surface is 2.8, and the average is 5.5, and the crust will have the lithosphere that is 40 kilometer beneath continents and 5 kilometer beneath ocean. If you see this diagram, okay, so here it is ocean, here it is continent. So this is that the lithosphere. So here in ocean it is 5 kilometer, and in continental crust it is 40 kilometer thickness. So 40 kilometer beneath continents and 5 kilometer beneath ocean. That is the thickness of your crust layer. Okay, so in ocean part thickness is 5 kilometer, and um, continent part it is 40 kilometer. And oceanic crust it is consisted of basaltic rocks, and whereas continental crust it is composed of granite rocks overlying the basaltic rocks. Okay. And the mantle it is 400 kilometer thickness. It is made of upper mantle. Upper mantle is 400 kilometer thickness, and it is made of olivine and pyroxene materials, and lower mantle is made of magnesium and iron oxide and quartz. The specific gravity of this mantle part it is 5, and the temperature inside the mantle is 2200 degrees Celsius, and the material inside is viscous semi-molten stage. Okay. So here it is solid, the material is solid. Here it is viscous semi-molten state, and the core, inner core, it is 1370 kilometer the diameter, and composed of iron or mixed with nickel and sulfur or silicon. Okay, so iron mixed with nickel and sulfur or silicon only. Here the material is different: magnesium, iron oxide, and quartz. Here it is iron oxide, iron and nickel. The temperature here it is 2200 degrees Celsius. Here it is 3000 degrees Celsius. And the specific gravity 9 to 12 in outer, and inner core it is 15. So that is why I already said in the beginning, the material and temperature, density, everything will be increased as you go deeper into the earth. Now, what is continental drift? Now, the Alfred Wegener, he discovered this theory, continental drift. According to his theory, the continents are the moving. Okay, so he presented the concept: the continents are moving. It is not the stable one; it is moving. So why? Because based on the 4 evidences, he come up with this conclusion. So before 250 million years ago, there was a supercontinent existed, which is he named it Pagaya. So the Pagaya is meaning it's the entire earth. So all the continents were present at one place, which is called Pagaya, that existed before 250 million years ago. Now, how he proved it? Based on 4 evidences, he proved it. This is that the supercontinent, which existed 250 million years ago, that he named as Pagaya. So the first evidence, the apparent fit of the continents. The apparent fit of the continents, that is, the coastlines of the continents appear to fit together like the pieces of a puzzle. So like if you see these two, the African continent and South American continent, these two fit. These two can fit the surfaces of this continent. The edges of these continents can fit. So that is the apparent fit of this continent. So it based on this is one evidence is previously these two were at the one place. And the second one, identical fossils. Identical fossils have been found in the rocks on either side of the ocean. Okay. So here and here, either side of the ocean and either side of the ocean, identical fossils have been found on the rocks of these places. That is the fossils of Cyanopenathus, then Mesosaurus. So all these the fossils of these species have been found in the many places. I mean, the coastlines of these places. And another one, identical rocks and mountain structures have been found on either side of the ocean. Again, the same identical fossils have been found on the either side of the ocean. Identical rocks and mountain structures have been found on either side of the ocean, like the glacier, the mountains have been found on these places. Okay, so it seems that these places were previously at one location. And coal has been found in the cold region, and glacial evidence have been found in the warmer region. That is the paleoclimatic data. Okay, so based on these the four evidences, uh, he come up with a conclusion that previously all these continents were at one place, but later all these continents were moved to the places where it is right now. Okay, so but based on his theory, he pres- uh, so later uh, he was able to explain the motion of the movement of the continents, but he was not able to explain at the end what force which was driving this movement of the continents. That was not he was not able to explain such theory. So now what it is? So we understand the continents are moving, okay, from the Alfred Wegener theory, but how it is moving? So that we will see from the plate tectonics and convection currents. Now, in the crust layer, the upper rigid layer, we have lithosphere, and the lower layer is asthenosphere, and it is 700-kilometer depth from the lithosphere. The lithosphere layer is 100 kilometer below continents and 50 kilometer below the oceans. Now, the lithospheric plates, these lithospheric plates, that is the plates, the crustal plates. So that will be floating on this asthenosphere, the liquids with a velocity of 2 to 10 centimeter per year. Okay. So if you see the crust, the plates on surface of the air, which is composed of n number of the small plates. But there are 7 major plates we have. That is one is Pacific plate, North American plate, two, and the South American plate, then African plate, then this one Antarctica plate, then Indo-Australian plate, and Eurasian plate, and other the small plates also present in it. So all these plates are moving uh, with a velocity of 2 to 10 centimeter per year. So these plates are floating on the that visco fluid material which is present inside the mantle. So how this movement of this plate is ensured? So one is due to convection currents. So that is uh, the thermomechanical behavior of their subsurface. That is movement of the less dense material, movements of less dense material to colder surface, and high dense material to warmer bottom layer. Okay, so less dense material will come up to the surface and it will get cooled, and high dense material, it will come down to the warmer plates. It will the difference in temperature, so it will based on the movement of these materials, it will create shear stresses at the bottom of these plates, bottom of these crustal plates, tectonic plates. Okay, so that is called the convection currents. This behavior is the thermomechanical behavior of Earth's subsurface. So you can see this. You can see here. So this material, it will move like this. This is the thermomechanical couple. Okay. So, and here also this material will moving like that. Thermomechanical couple will be happening like that. Here you can see here it will move like that. So when this movement occurs, it will create a shear stresses beneath the this crustal plates. Okay. So based on this movement, thermomechanical movement, convection currents, these are the convection currents. So based on this movement, uh, the plates are also will be moving. Okay. So this plate movement we have with a velocity of 2 centimeter per year. And during this movement, some of the lava, the magma, it will come up and it will again get cooled and solidified to form the crustal part only. Okay, and during this thermomechanical coupling action, convection current action, the tectonic plates, this will try to separate from each other, and in some other cases it will get collide with each other. Okay, it will hit each other. So because of this action because of this action, the continuous strain or stress will be built up at particular points of the edges of the plates, the plates. So you can see here this convection current will drive the movement of this tectonic plate. So during this plate movement, and here one plate will be there, here another plate will be there. When these two collide each other, there will be a continuous uh, development of buildup of strains at any one point. Okay. So when this uh, strain level exceeds the permissible value of the strain level of this rock material or the plate material, then definitely it will get exploded. Okay. So during that time, the earthquake waves will be generated. Okay. So that is called elastic rebound. So that we'll see next. So this movement of plate boundaries. So based on this convection current, how this movement of plate boundaries are classified. When these two are uh, when the movement of plate is away from each other, then it is called divergent ridges or it is spreading ridges. Okay, when these two are away from each other, when these two plates are moving away from each other, it is spreading ridges. When these two plates are uh, hitting each other or colliding each other, then there are two types of convergent boundaries possible. One is subduction and another one collision. When these two plates are of same material, then definitely these two will hit and strain will be built up at any point of these two plates only. So at this time, collision of two plates will happen. What about subduction? Subduction, if two plates are colliding, at that time, one material is of high strength material, another one is of the lower strength material, then definitely this high strength material will come above the this low strength material. So because of that, this subduction will happen. Okay? So one is subduction boundary and another one is collision boundary. And last one is transform boundaries. Here you can see these are the tectonic plate boundaries. Here this is called collision or divergent convergent boundary. This is called convergent boundary, and this is transform boundary. This is called transform boundaries. And yeah, this one is spreading ridges. This is divergent boundary, spreading ridges. These two, you can see these plates will be moving away. So that means the convection currents are driving this plate to move along this side and this plate to move this side. So because of that, at this location, the spreading of these two plates will be happening. Here you can see the convection currents will drive this plate and this plate to collide each other. Okay, so because of that, there is a collision boundary or convergent boundary will be happening at these locations. But here, this is irrespective of convergent or divergent, but this is something like shear kind of the movement. These two plates move opposite to each other, So that is called transform boundary. Okay. So in our Indian plate, you can see this is our Indian plate, Indo-Australian plate. At this location, Eurasian plate and Indian plate, it is colliding each other. Okay, it is colliding each other. The convergent boundary is occurring at Indian plate at this location, and here in this plate in the Indian Ocean at this location, it is creating a spreading ridges. Okay, these are the some of the figures to represent divergent, convergent, and transform boundaries. Okay, so this is called subduction. I said subduction. One material is of high strength and another material is of low strength material. Because of that, so one will go below to the high strength material. So here you can see the two plates because of this movement of the conduction currents. Okay, so these two plates are moving away from each other. You can see the ridges will form. The magma will try to come up. Okay. Mid-ocean ridge. You can see the Eurasian plate and Indian plate. I already said at this location there is a collision. Okay, so it creates, because of that only, the Himalaya, the height of the Himalayan mountain is being increased. Okay, so because of this two plate movement only. The ridge, divergent boundary, the ridge is exposed. Divergent means separating from each other. In mid-Atlantic ridge, this is a convergent boundary, that is subduction boundaries. Plates subduct, you can see here. When plates subduct, the trenches are being formed. Okay, and when there is no place to come up the magma during this subduction, some of the falls will be generated. The falls will be generated, or as already mentioned, at some point there will be the continuous buildup of the stress and strain. Okay, so when that the strain level exceeds the permissible strain level of this material, then the volcanoes or the continuous eruption of this magma is happening. The oceanic crust with the ocean and continental one convergent boundary. And when these two collide each other, then the formation of the mountains, small the mountains are happening. And this is with respect to continental convergent boundary. When these two continental plates collide each other, then at these two at the location of these two boundaries, the junction of these two boundaries, formation of the mountains happens. These are the plate tectonics map with the magnitude of the earthquake. This is 5.7 earthquake, 3.7, 10.5, 1.7, so like that. Yeah, this is about the movement of the Indian plate. Previously, the Indian continent, it was at this location about 71 million years ago. Okay, so India was at this location, but it was moving with the velocity of 9 meters per century. Okay, so now it moved 6,400 kilometers to the place right now. Okay. So 55 million years ago, it was here. Then 38, then it was at the equator. Then 10 million years ago here. Then right now it is colliding with the Eurasian plate. Now the plate movement reduced to 4.5 million per century. Previously it was 9 meter per century, because there was no such collision happened. Now, since the plate was colliding with each other, now the plate movement velocity is reduced to 4.5 meter per century. Now, because of this movement only, the lift of the height of your the Himalaya, uh, due to this collision only, Himalaya is also formed, and right now it is being increased every year. This is that movement of Indian plate and the formation of the Himalayas at the junction of Indian plate and the Eurasian plate. You can see here the Himalayas are forming because there is no oceanic crest. Both are continental crest. So previously we have seen at this junction there will be formation of the mountains. So it created the formation of the Himalayas. And this is called transform boundary. The example is the Pacific plate, that is San Andreas Fault. So the elastic rebound we'll see in next class. Anyone please take attendance? Jayesh?
Yes, sir, taken.
Yeah. Okay, any doubt? Anybody has any doubt?
No, sir.
No, sir.
Okay, thank you. Let me come again. Let me end this meeting and come again. We will discuss about the J component project.